Hey there. So this is kind of a interesting problem in the context of a lot of people that take this class are taking biochemistry sometime nearby it. And so this is actually a problem that's very important for biochemistry. So kind of a cool thing, a little intersections that you start seeing at the upper levels of chemistry and science. Anyways, so what you're looking at here is we have at two different pHs, we're going to be doing the structure of tyrosine. And, excuse me, tyrosine. I need something to drink apparently. Um, and there is essentially three points that could be protonated or deprotonated, right? Right here you have your carboxylic acid. Right here you have your, what would be an amine group. And right here you have a alcohol, and or a phenol actually in this case to be more specific. Um, and so these 3 points could be, well, an amine can be protonated, it's a base. Carboxylic acid is an acidic group, so at very, very low pHs it could take on a proton. Otherwise it's probably going to be deprotonated. This isn't going to be a low enough pH likely to deprotonate this group. Um, your most likely thing that's going to happen and is your NH2 right here. That's part of the amine, by the way. Right there's the amine, and this is what makes it tyrosine. That's the R group. This is the most likely one. This is going to be the first thing to get protonated. So automatically, this is going to get protonated first. Uh, so you're at low pH. Low pH means that it's an acid. This one is a high pH, 11.4. That means you're in basic conditions. And so what you should see is deprotonations. You won't have this protonated anymore. The amine will no longer be protonated. And this right here is actually going to deprotonate because this is high enough basic conditions. How do I know exactly for sure which one of these will protonate and deprotonate? Well, those are my Kas. So what I need to look at is I need to look at, for a polyprotic acid, we have our acid dissociation constants. Tyrosine will have 3 of those. It has a Ka1, and that's for this COOH, or in this case, because it's already deprotonated, COO minus, the carboxylic acid group. That you would expect to start deprotonating. Okay, so the COOH would start giving off its protons at any pH above 2.4 typically, 2.41 if you want to be more exact. You would start seeing a significant amount of deprotonation above that pH. Below that pH, you would expect to see the COOH, you would expect to be an H there. And that's because below that pH, you're going to have stronger acids. They're going to start putting protons on that group. The Ka2 then, the second one that comes off, is the amine, or in this case it's an ammonium ion, when it has the NH3 plus versus NH2, which is the amine. It's this group right here. So at any pH below 8.67, you would expect the majority of your species to be the NH3 plus. At any pH above the 8.67, you would expect the majority of your species to be the H2N, which is the amine that's been deprotonated. And then above 11, you would expect to start seeing this OH. And that's because it's Ka3 is the pKa third deprotonation would happen at pH 11. And you notice we're above pH 11.4, so the dominant species, the predominant species, will be the one that is fully deprotonated because we are now above all of the pKa's for this. If we had been below 11, you would have seen the H on here. Hopefully that helps and makes sense. Let me know if I was too circular in that, if you don't understand anything.